idea of bucket sort is really nice, but it still provides limited applicability on its own. Here we see how we can build up on the idea of bucket sort to come up with more general algorithms. We start by noting that bucket sort can be applied to sort keys of types other than integers. In reality, we can sort keys based on any given alphabet, as long as those keys can be indexed into a small integer range. In the bucket sort example, we worked with decimal digit keys, but we could potentially work with any of these other alphabets as well. Here we will also call our capital N the radix, which denotes the same as before for bucket sort, and that is the number of distinct keys we can have based on the given alphabet or range of keys that we are considering. Now for bucket sort, each element was connected to only one key, but imagine a situation where we now have composite keys, which are essentially d-tuples of elementary keys, such that each composite key will consist of a sequence of d elementary keys. For example, Dutch mobile phone numbers are 10 tuples of decimal digits because they are composed of 10 digits, where each of the 10 digits is in the range between 0 and 9. So the radix for this example is 10 possible digits per elementary key. Another example is airport codes. Each airport code is a 3-tuple of capital letters. This means that the airport code is composed of 3 letters, where each letter comes from the Latin alphabet in the range between A and Z, which contains 26 possible letters. And so 26 is the radix for airport codes. Now we are ready to define the idea of radix sorts. To sort a sequence S of n keys that are d-tuples each of radix n, what radix sorts will do is to apply the stable bucket sort algorithm sequentially using a different elementary key of the tuple at each iteration. How do you think we should process the elementary keys in the d-tuple? Should we apply it forwards, such that we first apply bucket sort to the first character, then to the second character, and finally to the third character? Or should we process the elementary keys backwards, such that we first sort on the last one, then we sort based on the second last one, and so on until we get to the first one? The answer is backwards, because if we first sort on the first key, once we start sorting based on the second key, we can destroy the ordering that was established by the first one, whereas sorting stably backwards will preserve the lexicographic ordering that we want. Lexicographic just means the way in which the words are sorted in a dictionary. This idea leads us to the first radix sort algorithm called LSD, where LSD stands for least significant digit first, not to be confused with the chemical substance. The reason for this name comes from the fact that we process the elementary keys backwards, starting from the least significant digit or key and ending up at the most significant digit or key. Here we have a small example where we are sorting 3-letter airport codes. So the number of digits or the length of these composite keys is 3. We are sorting a sequence of 5 of these keys, so small n is 5, and our radix, or the number of possible values per elementary key, denoted by capital N, is 26. Note that this is of course just a toy example, and that small n is usually much larger than capital N in real applications. So let's see how it works. We start with the least significant key, so the last one here on the right, and we sort based on that key. So our keys have been reordered in this way, and you can see that they are in non-decreasing order from top to bottom, if you only look at the last character. Then we proceed to the second character or key, and after we apply bucket sort based on this key, we can see that these keys are now sorted based on the last two characters. Then we proceed and apply bucket sort again, now based on the first character or key, and you can see that the airport codes are now perfectly sorted based on the three letters that compose their keys. So what is the time complexity of this radix sort algorithm? This is rather simple to derive because LSD radix sort algorithm is just bucket sort applied d times, as many as the number of elementary keys, and so the total time complexity will be proportional to d times small n plus capital N. One thing to keep in mind about LSD radix sort is that it generally works with keys of equal length. So it works for sorting strings of equal length, as we just saw here, integers of equal length as well, for instance using their bit representation or telephone numbers. In general, it can be made to work with variable length keys that align right, but then it will need to either process the keys per length or use padding with zeros on the left, such as you see here for multi-digit integers. It's not really suited for variable length keys that use lexicographic orders. So if you think of general strings of variable length, this algorithm wouldn't be the best for that. Let's go back to our original question where we were trying to figure out whether we needed to apply bucket sort sequentially by processing elementary keys forward or backward. We said that it wouldn't work if we processed the elementary keys forward or left to right. And here you can see that it doesn't really work because as you move from the most significant to the least significant digit, you can destroy the ordering that was established based on the previous key. And so at the end, you will not have a sequence sorted in lexicographic order. Can you think of a way to fix this and make this algorithm process the elementary keys left to right and deliver the sorted keys at the end? We can do that if we apply bucket sort recursively within each bucket formed in the previous iteration. So for this example, when processing the most significant key first, we would define these buckets. We would end up with these two keys in bucket A, one key in bucket B, one key in bucket L, and another key in bucket Z. So if in the subsequent iteration, when processing the second most significant key, we now apply bucket sort recursively within this bucket, we will make sure that only the order of the elements in this bucket will be affected. And that's okay because we know that if these keys are in the same bucket, then it's because all the elementary keys that come before the key that we are processing are the same. Otherwise, they wouldn't be in the same bucket. Here we don't need to do anything for the other buckets since they only contain one element and so they are sorted by definition. So if we apply bucket sort in this way, we can definitely sort by starting with the most significant digit and ending at the least significant digit. This also leads to another important result, which is, as you can see here, some keys may become sorted even before we have processed all the elementary keys. MSD radix sort works with keys of different lengths, like general strings, while still working for integers because it can make use of their bit representation as well. Asymptotically, the time and space complexities of MSD are the same as the ones for LSD, but in practice there are two things to keep in mind. One is that MSD can be faster than LSD since it may not need to process all the elementary keys as we've seen before, and as you can see here also again in another example. But the drawback of MSD is that it's a recursive algorithm while LSD is non-recursive, and so the MSD algorithm can have quite some overhead due to recursive calls. As you might expect, these performances can be improved by combining ideas from different algorithms. We will not cover them in this course, but if you're curious, you can check, for instance, the three-way radix quicksort algorithm. Here you can find a summary of the most important properties for all the sorting algorithms that we've seen, now also updated to include a column about their stability and also a row for the radix sorts algorithms. We've already discussed the other algorithms at length. Here I just want to add that radix sorts are suited for sorting integers, strings, as well as other d-tuples. Radix sorts can be faster than comparison-based sorting algorithms as long as d times n plus capital N stays comfortably under n log n.